Thank you. So, hi everyone, my name's Sasha. I'm a PhD student at Queens. I actually submitted my thesis just last night. So I finally got some sleep, and now I'm awake and ready to tell you about the benefit of transitioning. This is a technique I used in a recent paper, and I was really happy about it. It's sort of a soft spot in my heart. I really want to tell you about it. The objects I'm interested in here are vector bundles. So if I have a vector bundle of rank R and a variety, really I can think about it as I take some open cover of my variety, and on each open, I just cross it with a vector space. And so I have a bunch of these charts. I want to glue them together. And so to do that, I just need to tell you how to change one basis to another basis. And I do that with this transition matrix. And so the transition matrix will have entries which are sections on the overlaps. And so in general, these are going to be polynomial functions. With Brett, who's going to be at McMaster with me next year, we were interested in considering surjective endomorphisms of the projective bundle. So one thing you can do with the vector bundle is, all of the fibers are vector spaces. You could just projectivize those and get a projective space. And if you do this in sort of a global way, you get a projective variety. And I was interested in self-maps of these things. To describe the self-maps, one way you can do it is to use the transition functions. So this is sort of the explicit part of it, that on the projective spaces, to describe an endomorphism, you just need to give a collection of polynomials which don't have a common zero. So you can do that for each one of the charts. You do that, and then you just need them to glue together using the transition matrices. So that's the commutativity of this diagram. If you know the formula for the transition functions, you just need to check that this diagram commutes. But one thing which kind of surprised me and was kind of interesting was that there's also an implicit one. So if if my vector bundle is actually a direct sum of line bundles, I don't even need to know the transition functions to be able to make a conclusion. I just still check sort of what does it mean to have sort of a section using the transition functions, and I can actually make conclusions just with that. And in particular, in this case, for the projectivization of a direct sum of line bundles, for it to have an endomorphism, it requires that the bundles are torsion. It's kind of interesting. So using these two approaches, we were actually able to prove something called the Kawaguchi-Silverman conjecture for projective bundles on elliptic curves. I won't tell you what that is. You can ask me after if you're interested. But it was one of the sort of long-standing, this is a sort of recent conjecture, but this was one of the open cases that people couldn't do with sort of a lot of the sophisticated machinery, but we were able to do it with transition functions. Okay, and that's it. Thanks.